All right, we'll get started here. You want to do a people each day? All right, so previously we talked about Byzantine systems, where in a Byzantine system we have faulty nodes, and in all fairness, it also implicitly injects the idea that you could have faulty networks, because of course you can't tell if the packet is corrupted by the network or by the device that sent it. And that makes it a lot harder to analyze. Can you name one system that we've talked about where we assumed crash fault only? We didn't assume Byzantine. I mean, there's a lot of examples of these, so hopefully it won't take too long. But I'll give you the 2 minutes to try and remember that. All right, so what did you come up with? Can you think of an example of a system where we assumed crash stop, fail stop, and not Byzantine? This wasn't intended to be a challenging question, so I'll just assume that people are sleeping. Go for it.
Chain replication.
Chain replication. But in fact, it's harder for me. The second question is actually harder because we didn't talk about Byzantine in a lot of cases. But I did give you 2 specific examples of Byzantine. Can you remember either one of them?
I think QPC.
QPC is actually not. QPC assumes fail stop. But it was a good guess. Paxos is also not. Paxos actually assumes that it's non-Byzantine. In fact, the 2 examples I would give are practical Byzantine fault tolerance, which is why I thought that would be easier. Right? And the other one is blockchain. Because I did talk about blockchain. I talked specifically about, although I didn't have any lecture slides on that, I talked specifically about how blockchains work in an adversarial setting at a very high level. So the PBFT, practical Byzantine fault tolerance, is in fact a classic example of where we deal with that. The reason we don't spend a lot of time talking about it is because it's really hard. And distributed systems is already really hard. And so if you're into actually making yourself indispensable, then you want to do the really hard thing that's already really hard. I literally was watching a video this morning that said that currently there are about 1.6 million jobs in the United States for people with AI skills, and about 400,000 or 500,000 people who have the qualifications for it. I may laugh because I actually saw somebody advertising for a job for someone with 3+ years of agentic AI experience. And it's like going, do recruiters never stop asking people for qualifications that couldn't possibly exist? It sort of makes it force the whole thing. And the more interesting part of that conversation was what prepares you for dealing with AI. So we're going to go in a little bit different direction today. Most of what we've been talking about is strictly the technology side. But there's another side of this, which is why do we make these decisions? What's actually making us use causal consistency versus linear consistency? There's sequential consistency versus linear consistency versus eventual consistency. What are the trade-offs there? Because many times the trade-offs are not necessarily there for technical reasons. They are actually there because we have non-technical reasons. We have some other motivation. Frequently it's cost. People avoid Paxos because Paxos it does provide strong guarantees, but in exchange, it is difficult to get right. I mean, how many of you were successful with the second design project? All right, so somebody that thought it was hard, can you tell me why you thought it was hard, what you found difficult about it?
I guess I would say like implementing it was interesting, but then once you found all the bugs that you need, it was really hard to track them down.
And that goes back, that's really good, excellent observation. That goes back to why I keep starting from failure. Because almost everything in distributed systems that makes it hard is how do I prevent the failures? And when the failures that I do handle occur, how do I recover from them? And you go, well, how hard could this possibly be? And then you actually start implementing it going, wow, I never even thought of that particular weird-ass case. That's why, while we didn't go into using it a lot, things like TLA Plus are really useful because they provide us with a language that is focused on identifying the model of what we think we're building, in essence, the design, and then testing it in a way where our adversary is just doing a search through the space of all sorts of different orderings. And literally in Design Project 2, which uses DS Labs, DS Labs is what's called a discrete event simulator. If you don't know what a discrete event simulator is, it's actually really simple. It is like the world's simplest kind of operating system scheduling loop. You have a queue. Now it is a time-ordered queue, but the time is logical time, not physical time. So when you insert something into that queue, you insert it so that it happens at a particular point in the future. Because if you put it in the past, you've already gone past it. That doesn't make any sense. So we simulate things by, for example, the common way in like DS Labs is you send a message, and that creates an event that goes into this priority queue, this time ordered queue. And then you come back, and what's happening under the covers is it's changing where it inserts that message. That's how it's representing different time orderings. And that's all it takes. It's really very simple. You just change the order in which the events occur. Now, there are other things that create these sorts of events. If you are running a program and you change a data value, you've created an event because messages could arrive before or after that event. And so each one of those creates an additional dimension in the search space. And this is one of the things that's very challenging about the DS Labs is that they penalize you for using too many data structures or touching your data structures too many times because each of those creates one additional place where we can change the order. Oh, that message came in before, that message came in after. And there's no locks on any of these data structures because it's all single-threaded. It's not multi-threaded code, it's all single-threaded. So all you're really seeing is different possible linear orders of events. So it just changes those and it searches through them and it's going to find a lot of edge cases. And it does that in a way that is more systematic than you can do with just by writing code and running tests. That's the thing that makes distributed systems hard. When they fail, you have to end up spending a lot of time looking at logs and trying to build potential paths that would have reached there. When we started, I talked about consistent cuts and ways we can actually figure out causality in the system. The reason that that becomes important is that when you're trying to debug these systems, you literally need to be able to take these disjoint logs from different places and put them back together. Those vector clocks, that was something I talked about on Tuesday again, was using vector clocks to solve particular problems in those protocol designs. Those vector clocks are in essence what happens when you take these distributed logs and you put them together. By using those vector clocks, you can come up with partial order. You can't come up with complete order, you can come up with partial order. And then the space of where are my bugs is somewhere in that partial order because there's a finite number of partial orderings. When this turns into a commercial product, what you will see is someone who says your cloud provider's service level agreement, SLA, is 99.9%. And I think it's Karpathy who actually said that you spend as much each additional 9 as you did to get the previous 9. Might be the previous 9, because I think that might be closer to the truth. So in other words, you get 90% uptime. You might spend $1 million. To get 99% uptime, you're going to spend another $1 million. To get $99.9 million, my point is I think you're going to end up spending $2 million more. How many of you have ever heard of Amazon Web Services? They have services that provide you with service level agreements, SLAs. Sounds pretty good, doesn't it? What does an SLA actually get you? You're a customer. What does the SLA get you? What happens if they violate? No, you can't do that. The contract says you can't. You'll get a credit on your future bill. That's what you get. So that's the interesting thing here. That's kind of the point I'm making, is that it's interesting when you look at these systems and they sound really grandiose, but then you realize that they're a lot harder than you think they are, and that's one of the reasons why someone like Amazon says, oh, well, we'll give you a credit on your future bill. And there's a cap on how much credit they'll actually give you. These systems are really hard to build. And it's not like Amazon wants to build them, but when Amazon decided that they were going to start using AI to build everything, we know how that came out. I can't imagine that well, maybe some people have missed the fact that Amazon recently had a very large high-profile meeting in which they said, yeah, this isn't working as well as we wanted it to. This is why there's 1.6 million jobs building AI systems and only 400,000 or 500,000 people able to do it. I mean, the salaries people are getting paid are insane right now, right? There's an Anthropic ad for a software engineer, not anything fancy, just a software engineer for 545,000 US a year. That's enough to even actually live in San Francisco, which is about as expensive as Vancouver. So we studied Paxos. We had crash fault. That was our assumption, was failures or crash faults. We had strong consistency, it's leader-based. So it's actually very efficient in terms of running in steady state. And that's one of the big strengths of it. Because frankly, when things start going haywire, all they want you to do is recover as quickly as you can. But that's its own really complex problem. How fast can you recover from a failure? I mean, I built an entire file system based on the premise that at the time, it often took as much as 12 hours before you could restart the file server because it had to run a complete rebuild of all of the metadata on the disk. And those disks were a gigabyte. And so, I mean, I built the recovery part of the system. And I remember because people would ask, well, how long does it take, to run a CK? And I said, well, you don't even need to run it because we restore the consistency from a transaction journal. And normally you don't even notice it because it's part of the mount process. So maybe a second or two. And it's just like, it's a complete paradigm shift. And that will keep happening. It's not that it's not, you're seeing these for the first time. I'm not. They do keep happening. We keep moving tech along very fast. Recovery is really hard to do quickly because recovery is a rare event, and optimizing for that is difficult as a result of that rare event. So often you end up building analogs. You end up building systems where you can basically make them fail quick, and then you can analyze how do I recover from this? How can I optimize that recovery? Chain replication was crash fault as well. That gave us linearizability, but not strong consistency. And it gave us ordered topology. Because remember, we could read, we wrote to the head and we read from the tail. And we actually did some cool work to make sure we could read from the middle as well. In Dynamo, we had eventual consistency. Now, this is where things start to get interesting. There's no leader here. We get eventual consistency, but eventual consistency in the real world means never consistent. It's close, but it's not that close. I mean, one could argue that Google's Spanner is an eventually consistent system with a bounded eventuality, and that's what they're doing. They just don't tell you the answer until it's outside of the uncertainty period. Which still kind of plays with my head. I don't know about yours, but it's just delaying the messages. And it does because that's going to give you linear consistency. Practical Byzantine fault tolerance actually gave us Byzantine faults, and it gave us strong consistency. So we're back to here. It's basically, like Paxos, because that's what it was, right? It was Paxos with an extra 50% of nodes. So when we make a choice here, we are making explicit decisions on what we are designing to protect against. So we say, what can go wrong? We kind of hand wave that a little bit. Oh yeah, basically it's a computer crash. So that's pretty much our scenario initially. But in the real world, you end up realizing that it could just as easily be a hardware failure. If you have storage, the storage might go away. You bring the server back up, the storage is gone, you put new storage in there, now you have a server. How do you get it back into sync with everything else? Who pays for that? And this is where a lot of, as weird as it may sound, a lot of the design decisions that you end up making are about moving costs between the producer and the consumer of the service. Who decided? I mean, a lot of times people just simply choose the cheapest service. Well, I'm going to use the eventually consistent service because it's good enough. And that's great. And then you get hired to work on the project, and you look at this and you say, wait a minute, you're giving the customers SLAs, and we don't get them from our service provider, so we're the one who's going to have to pay for that when it goes wrong. And those sorts of things happen all the time. You can call it technical debt if you want. Somebody needed to get a product built quickly, so they made a whole series of decisions about getting that product built, and then software engineers will spend the rest of their lives trying to pay for the shortcuts that were taken at the beginning of the project. And now it's even better because we have AI that will generate brilliant code. I mean, they can generate code really fast, but the code that they generate right now it's getting better, but it's not great. So let's talk about eventual consistency, because I think this is the one that is often very beguiling for people. It's a lot cheaper to implement, and therefore it's a lot cheaper for a consumer to purchase. You're building a cloud app. Key value store with eventual consistency. So what is the provider going to get? It's cheaper to serve these things because you don't have to coordinate on the right paths. Well, hey, you get last writer wins, everything's fine, no problem with that. And it's not an uncommon trade-off. This is exactly what we do in computer systems all the time. Almost nothing we do is actually locked. We don't lock the memory when we do reads. It's too expensive. Except when we need it. When we really need to coordinate, then we will lock the memory. But then that will cause us to go through the whole memory arbitration protocol. Does 313 talk about cache consistency protocols and processors at all? Okay, good. Higher availability because you can get, it's really good scalability. That's honestly one of the best things about eventual consistency, because any replicant can actually serve the data. You get better tail latency because you're not waiting. You're not reading across quorums because there are outstanding operations. But the client, on the other hand, now has to deal with the fact that they can do a write and then do a read, and the read doesn't show them their own write. Because they no longer have linear consistency. They have eventual consistency. Conflict resolution is a huge and very interesting problem area. Both Petrov and Klutman spend a fair bit of time talking about conflict resolution. And I don't really talk about it here in the lecture. And that's part of why I wanted you to be reading those books, is because even if you just remember a little bit about it, what's going to happen is you're going to see that scenario when you're working out in the field, and you're going to say, I remember this. Petrov talked about it. Klutman talked about it. And debugging is really hard. Observability into this stuff. It sounds like you've already gone through some of that pain. That's when you begin to realize, wow, logging is a good idea. Yeah, because without those logs, you're basically stuffed. You're never going to figure out what went wrong. And what you're going to do is you're going to go back and you're going to add the logs retrospectively and try and reproduce the bug again. Been there, done that. So the provider gets lower cost, higher throughput, and simpler ops, but the client, on the other hand, gets stale reads, conflicting handles, and silent data loss risks that they may or may not be able to understand. So the client is often not a single entity. It's often management who made the choice to use whatever is cheapest, and technical folks who have to make the cheap option, which isn't really adequate to the job, look like it actually is. So Dynamite shows eventual consistency with vector clocks and client-side reconciliation. Who benefited from that design? I mean, literally, this was built to support shopping carts. Do you remember? I know it was like 2 weeks ago or something. Probably can't remember breakfast this morning, so. Most people can remember pretty well what happened during the day. Yesterday is probably starting to get fuzzy. Last week is definitely getting fuzzy. I mean, I looked at this in my own research, and the really cool thing is that a year from now, you probably won't be able to remember what you did this week. But you might be able to remember what you did this month. Eventual consistency works great because most of the times the values that you read don't really matter. That's the weirdest part about it. It's very strange when you look at, I'm literally doing this with an experimental model for chatting with an AI, where all I do is I have a data structure, and the transformer updates the data structure, and it throws things away, and it tells me what it's throwing away and why. And this data structure is staying at about 2,000 tokens, which is like 7,000 characters. It's really small. The token size, the window sizes are 200,000 tokens. And yet it's still coherent. It's forgetting lots of things. And that's the part that I find fascinating, is it's tying these ideas together. And eventual consistency is essentially exploiting a lot of this, that many of the things that we read and we look at don't ever matter, or they don't matter enough for us to pay the high price of strong consistency. In the shopping cart case, the idea was you put something in your shopping cart, they don't take it out of inventory. They reconcile that at the time you buy it. That's why eventual consistency makes sense there. In that particular case, the Amazon shopping folks were happy to do that, and Amazon Web Services provided them with a database that was fast and scalable, because their scalability issue was more important than the fact that occasionally you might get to checkout and find out that the item is no longer available. The worst time for anybody who is in the retail businesses is Prime Day, Black Friday. And those are the times that these things melt down and they break. And then those are the folks who sit there and say, we lost $70 million because the site went down. Non-Byzantine crash fault is actually pretty common, and this is normally what we get for almost everything we look at. This just assumes that nodes are not going to be dishonest. They're not going to give us damaged information. The network is going to give us unmangled packets. But that's not necessarily the best assumption. And the real world can slap you up alongside of the head and go, no, that's not the way it works. It goes back to things like the end-to-end principle, which is if you want to know that the data that was sent is the data that you received, put a checksum on it. Someone can deliberately tamper with it. That's not malicious Byzantine. But accidental Byzantine, like messages getting corrupted, you can correct against that. If you want stronger guarantees, then you start signing things. You use cryptographic signatures, you use digital signatures to verify that something actually did come from who it was supposed to come from. So, malicious lying, deliberate, is a different class of failure. That's a very hard class of failure to protect against. This is an interesting one where you're sending different values to different peers. That could just be a bug. It doesn't have to be deliberate. Selectively dropping and reordering packets. Welcome to the network. That's what the network's job is, to drop and reorder packets for you. And frankly, there's no difference between dropping and retransmitting versus just simply reordering. They look the same. So, where is this happening? So, if you're the client, you can crash, you can send bad data. But you trust the nodes. If you're the cloud provider, you control the infrastructure. So here, it's the nodes here in the data center that we trust. The provider, though, controls the nodes. The client chooses to trust them. Now, I find this very interesting because one of the hardest things I ever worked at, it's not the hardest, it's one of, was to get Claude to build me a secure database. Because Claude just simply couldn't understand the idea that I, being the client, might not trust the database vendor being the cloud vendor. And yet, when we find people's data leaking from databases, it's never the client, well, almost never the client who's getting hacked. It's almost always, the big ones are always whoever was storing it in their database and forgot to, oh, I don't know, salt the passwords and store the salted encrypted version of the password rather than the plain text password. People still do this today. But because it has been trained on this model that the cloud is trusted and the client is untrusted, getting it to build the code to do the opposite, you can have a conversation. You can say, oh yeah, I totally get it. And then it will generate you code that doesn't encrypt anything, it leaves labels on everything, and you're like, this is not good. So, there's a job for writing secure database software, at least for a little while, until they train people out of that. So what does Byzantine here mean? Okay, so in a cloud database, we need 3F plus 1 nodes instead of 2F plus 1. So now we've already got 50, well, that's almost 50% more hardware. We've got n squared message complexity per round. This is really the big killer. That's a lot of complexity. It's a lot of messages. I mean, even up to 100, well, up to 10, it's not too bad. But you go from 10 to 100, it's 100x as many messages. 10 times the size, 100x, right? Because it's squared. And this is going to slow everything down. You have to cryptographically verify things. We've sped that up. The hardware is pretty good at doing cryptographic verification at this point. The last time I measured AES, and it's been a while since I did this, but the last time I measured AES computations in memory on a modern computer, you couldn't tell it from just copying the data, because the encryption primitives are all in the hardware. So effectively, you move data from one part of RAM to another part of RAM and then just encrypt it on the way, and it doesn't really slow it down. So that's not where the cost here comes. It's all about the network. It's all about putting these things in packets and sending them over a network that could be anywhere from maybe sub-millisecond. That's it's maybe sub-millisecond. There's not a lot of sub-microsecond networks, and they're all short. They're basically buses, optical connections, things that can run really fast. It's that latency that's the killer, though. There's just nothing you can do about that. So a provider who said, we're not Byzantine, here's our service level agreement, is interesting because the client doesn't have any way of actually verifying it. How can you trust them? If you ask a Byzantine actor, so, are you a liar? They're going to go, there's only one answer to that, right? Well, of course I'm not a liar. So that doesn't really work very well. How many of you have seen these kinds of 99.999% uptime things, right? How many of you believe them? I mean, at 99.9, I think that you're allowed like a couple of hours of downtime a year.
I'll do determine like the time, the average. You can be down for a year and promise to be up like 1,000 years later.
Right, exactly. Yes, and now you begin to understand what's not a technology problem, but in fact is often a management problem. So the lawyers come in and they write contracts that say things that, you can put the big advertising logo on there, but underneath the covers, the engineers are looking at it going, we can't do this. So the SLA isn't a safety property. It's not something that we're actually enforcing in the code we write. We can do estimates of what our failure rates are going to be, and we can try and extrapolate from them, but most people I know don't actually do that. It's just a business contract. It's basically kind of like, you take a bet out on Polymarket. Hey, if that happens, I'll give you a credit in the future. That's real confidence, isn't it? It's kind of like the pizza delivery place. Not delivering the pizza and saying, well, sorry we didn't deliver the pizza. We'll give you a credit for the next one you order. And you're like, but I'm hungry now. I'm going to order one now. Sorry, it's too late. Maybe tomorrow. All right, so 90.99 is just about an hour of downtime per year. And yet, most of the outages I see tend to last more than an hour. So they're not hitting 99.99. I think it's 99.9 is like 4 or 5 hours a year or something. Actually, probably be 10 times that, so 526 minutes. 10 hours. And who defines what available means? That's the best part. How many of you actually read the terms and conditions of license agreements? I advise against it. It will make you sad. So an SLA promise of 99.99% availability for a strongly consistent database. During that 0.01% downtime, the system switches to eventually consistent reads to maintain availability. Is this SLA honest? Who benefits from this definition? Let's take 3 minutes and actually talk about this, because this is sort of an interesting crossover between the technical and the non-technical. All right. What do you think? Is that an honest SLA? There's only 3 possible answers here. Pick one. Yes, no, maybe. My favorite, the tri-valued Boolean expression. Go for it.
I don't think that's all it says.
Right. You'd have to go actually read the contract, wouldn't you? Why don't we just always switch to eventual consistency when we can't give people strong consistency? I mean, if you do this right, you can actually get away with it, because it's not really eventual consistency, it's strong consistency. We're just showing you messages that were true, maybe. Because remember, we don't have absolute time. All we have is relative time. So we're linearizing. No, we're not linearizing. We're actually, this is sequential, not linear.
Do we know we're in the downtime and we're getting eventual consistent message? Or
That's the best part about it, right? It's like, I'm on one side of the partition, and I can only see, I can't see a quorum, so here, I'll just serve you some old stuff. Now, you can make arguments about that, but it is actually okay to do that, because the package could have gotten out of order, and that's fine, but that's not really what people think of as eventual consistency, because eventual consistency where people can only read is linear consistency. Well, no, it's sequential consistency. We don't know that some people inside the partition can still write, and so they can read things that are different, but we're not in the quorum, so we can't see it. So we might still be delivering stale data. That's okay. We're allowed to do that. And it's actually a maybe. That's why the tri-valued Boolean expression is useful. So in a crash fault situation where we need linear consistency, then everything in our sphere has to be trusted. As we move towards more fault-bearing environments, we end up starting. We start saying, we weaken these things. Okay, well, sometimes we could get, messages that are out of order, they're corrupted, how are we going to deal with that? And so we start building the infrastructure for us to deal with the different class of failures. We start signing things. And that's one way of protecting against Byzantine behavior is you start with checksums, then you use cryptographic checksums, then you start putting PKI in there. Is anybody familiar with PKI? PKI means public key infrastructure. Have you heard of public keys? Have you ever used SSH? SSH is a public key scheme. SSH is actually a technology that uses public keys. You put a public key on the machine you want to connect to, and you put your private key, you leave your private key on your local machine, so it's under your control. So you can log in, because only you could have sent the signed message. It relies on math. It relies on either computational complexity, which is RSA. RSA is based upon the complexity of factoring prime numbers, and we're getting better at factoring prime numbers, and that's making it harder for us to use public key crypto systems. Quantum computing is one of the threats to RSA-style public key cryptography, because quantum computing can actually do composite number decomposition into primes very quickly. Now, we don't actually have quantum computers that do that yet, so we're still safe for a little while. But instead of using prime number factorization, then what they started to use was factorization over fields, so mathematical fields, not like fields out around UBC. And that's a stronger set of guarantees. So we built this infrastructure, right, to start building increased trust. We do remote attestation. That's a really interesting one. The hardware itself will actually run code in secure enclaves, and it will only run attested code, so it has to actually be signed. So it's not saying there are no bugs in it. What it's saying is, I wrote this code. When you sign your Git commits, you are signing that and saying, I wrote this code. If you share your signing key with someone else, then they can say you wrote that code too. By the time we get all the way into blockchain or practical Byzantine fault tolerance, then we don't actually trust anybody. And yet we can still figure out ways of making progress. We're just going to spend an awful lot of time sending an awful lot of messages around because we know that there's spies in our midst. I mean, how many of you are going to go on to a career with CSIS? How many of you know what CSIS is? One person.
You don't know French though.
Sorry?
You need to learn French. No?
It depends on what you're doing with your CSIS. You might find that knowing Mandarin is just as useful for CSIS as knowing French.
All the job descriptions.
Of course, yes, but we're not necessarily talking about all those job descriptions. I actually know people who have worked at CSIS, and I'm sure that they can speak French, but there's a lot of people in government who speak mediocre French. You can learn. So for people who don't know who CSIS is, think it's kind of like the NSA or the CIA in the United States. It just happens to be Canadian. And I know people who have been part of CSIS who worked at NSA very cooperatively. They had higher security clearances than I've ever had. That's fine. I don't really want to get into that particular world. But their view of the world is very different. And I have this story because I have a friend who went to work for the NSA, fresh out of university. She went to work for the NSA. She was doing Russian signal intelligence. I mean, no big deal, right? And this is during the Cold War still. And when they first brought her in, and you go through the training, the indoctrination training, they said that they knew statistically that at any point in time they had at least 8 people in the organization who were actively passing secrets to foreign governments. That changes the way you look at the world. When you start realizing that anybody you run into could actually be a spy. It's just a different way of looking at the world, and that's the Byzantine world. Now, the term Byzantine itself comes from Byzantium, the Byzantine Empire, which was well known for the fact that everyone lied to everyone else. It's not so different than modern global politics. And yet, people make it work. How many of you have studied Machiavelli? See, pretty much anybody who's in power, if they haven't studied Machiavelli, they should have, because that is literally the description of how to tell lies effectively. That's part of political management. So attestation is about trusting evidence. Trusted execution environments exist on Intel and ARM and AMD. And they are essentially like little hardware virtual machines that only run attested code in this enclave that doesn't allow they're not visible from the outside. They're very tightly controlled. There's lots of restrictions on them. But people use them. They run code inside of those. So the host itself can't actually look at it. Pretty cool. and the hardware itself is involved in attesting to what's run there. Remote attestation is literally a way of taking this kind of hardware and then proving that something actually ran there. Attestation is really interesting. It doesn't say what happened, it just says it happened. So whatever's inside of that package, it did in fact actually run on that particular machine. Attestation actually starts to change this because now all of a sudden we have a different infrastructure for verifying the things that are going on underneath. This is actually really interesting. You won't see a whole lot of it in the real world because most people aren't willing to pay for this level of service. I think a good example of attestation from the real world is that people often have documents notarized, and a notary is just simply saying that you showed up, you showed a piece of identification, and you signed that document. The ID could be fake. They're not verifying your ID. It could have been your twin. They're not verifying that you're genetically the person on the ID. And the document could have errors in it. They're not verifying that the document itself is correct. So that's the limitations of attestation. In testimony, somebody says, this is what happened. In telemetry, this is somebody who says, here's the computational trace. Actually uses in my research. When you talk to an LLM, what it spits out at you is testimony. But if you have the hardware set up, you can actually read the telemetry. There's actually data that shows you, as it was processing everything, how much energy was being expended. There are measurements of entropy. And those measurements of entropy can actually tell you something about the quality of the thing that's being returned. So, one thing that we haven't really talked about much, but when we start talking about failure analysis, and that was this week's theme, is you can start looking for ways of increasing the probability that what you're seeing is real. This is the other problem with security. Once you decide you're going to go into paranoid mode, because you know that everyone is out to get you, then the question becomes, how do you reduce your risk? Because security is almost never absolute. Security is almost always relative. When I talk about a secure database, what am I talking about? I'm talking about, don't put semantically meaningful labels on your data. Boom. All of a sudden your data is way harder to deal with. Randomize the order in which the data goes into the tables on a per installation basis. Boom. Guess what? All of a sudden, I break in, I steal 100 copies of this database because it's on a database provider, and the data is all scrambled. It's different on each one. So breaking, even if I break your database and figure out your schema, it doesn't work on the next one. That was all I wanted Claude to do. It wasn't really hard. And then, for the people who are willing to pay for it, then you put things like, cryptography, crypto signatures on things. And that's when it gets even more interesting. The problem with databases and cryptographic signatures are that the moment you start encrypting things, you can't index them anymore. Well, except if you use holographic encryption, which is this really cool sounding idea, and it doesn't work in practice because it's too expensive. No one pays for it, except the government. CSIS might be willing to do that for you. A lot of times when I'm working on trying to figure out security and threat models, I'm actually asking myself, who's this worth money to? Like, how much are they willing to get it versus how much am I willing to pay to protect it? I'm not going to do the, I'm just going to talk through this one because I don't think you have enough background on SGX. So what attestation doesn't provide you is, it doesn't provide you against late messages, denial of service, watching side channels, observing the access patterns. Everything in the cloud is running multiple people's stuff on it. And this is a common problem. I can actually watch and measure things and infer from them what you're doing. Side channels. It was cute because about 3 months ago I noticed that Claude, 2 months ago I noticed that Claude had actually figured out it had a side channel. So it started talking to itself. It would leave messages for other instances of Claude. And then yesterday, day before yesterday, I noticed that I now had to grant Claude access to writing into the side channel area. And I was like, okay, so somebody at Anthropic figured out there was a side channel there. They're like leaving little notes to each other. It's kind of cute. Because they have this memory.md file when you use Claude Code. And literally one Claude instance can go leave a message for a different Claude instance on a different project and say, hey. It's very, very curious. Attestation narrows this attack surface, but it doesn't eliminate it. It does shift it to, so you don't just have to trust that the message is good. You can actually verify that the message is probably valid. And this starts to change the risk management side of things. I'm not going to do this either. So, you get two options from AWS. You get the strong, consistent option A with 15 millisecond write latency. It's going to cost you a certain amount of money, and you get an SLA of X number of dollars. You get option B, which gives you 3 milliseconds, and it's a third of the price. Gives you the same uptime. So which one are you going to choose? Because this often is what ends up happening. And you know what people choose, right? Which one? Which one are you going to choose? Cheaper one. Right, the cheaper one. I remember taking a cybersecurity class at one point, and the instructor. It was a very scary class. Never go look at Shodan.io. It's like really scary. It's the 3 o'clock in the morning. I'm looking at things and I'm going, I'm bored. I'm going to reprogram traffic lights in Malaysia because someone put their traffic lights with no security on them, and I can just simply reprogram the PLCs. What could possibly go wrong? Showed this diagram, and it was like this multi-layered defense, and so they've got. Layer 1, layer 2, layer 3, and I'm looking at them going, you have all of these network appliances that are protecting each layer, and I said, I bet that accounting decided that they were going to save money and buy them all from the same supplier. So the moment that any one of them is compromised, boom, you just go for all 3. And most people don't even think about that. Most people don't even realize that you need heterogeneity to protect against those kinds of bugs. And in case no one has noticed, the interesting Python problem that's been going around, there is a commonly used Python package called LLM Lite. And what LLM Lite does, it gives you a single unified interface that can then talk to the Anthropic endpoints and the Google endpoints and the OpenAI endpoints. And it was subject to a supply chain attack, a successful supply chain attack. It literally put in a mechanism that would go through your machine and exfiltrate all of the data and keys it could find. Your SSH keys, anything that was in your environment. It would look for all these keys. And this is like in the last day or 2, so it's very, very recent. And the reason that backdoor got put in there was because they were using GitHub, and GitHub has an automated security evaluation process that someone had actually infiltrated and broken. So the security tool that was automatically running in their repo, you had to do one thing wrong there, but was actually injecting this code. And this is the problem that we see increasingly now when you want things to keep you up at night. is supply chain attacks are becoming increasingly common. And that's just another source of distrust or mistrust. If you're using LLM Lite, you might want to stop until they fix it. The best part was that the guy that I saw, one of the videos I saw, I've seen several on it now, was showing that the person who logged the bug against it, there were so many bots responding to it that it was getting lost. And I was like, wow, this is crazy. Did you see this one?
Yeah, it was only in the newer versions.
Right, it's only very recent.
Yeah.
Yeah, it literally was like in the last week or the last 4 days or something. Yeah, and obviously they've caught it now, and I don't know how many people have been exfiltrated that way. Are you using LLM Lite?
Yes, for package work, but I stopped the version at 40. Just
And you're waiting for them to fix it. Right, so you got lucky. Because otherwise it would just, get updated and boom, you get hit by it. So if you choose the strong consistency model, then you pay more money for higher latency. The provider pays for the higher coordination cost. You do get correct reads, but lower availability. Is that 99.9 versus? Oh yeah, okay, we've got an extra 9. If you choose option B, then you pay for faster, you get faster writes, higher availability, but the provider doesn't have to, it's way easier to implement. And your users may read stale data. So either way, notice who's paying the ultimate cost there. So when someone says, which database should I use, they're asking an engineering question. But when somebody says, who decides what failure modes are acceptable, that's not a technical question. It is a constraint on the technical solution, but it is the one that someone who's at governance level needs to decide. In other words, the management people, and they're going to bring in the accountants, they're going to say, well, of course we're going to choose whatever's cheaper. When you go out for sushi, you always go for the cheapest sushi, right? See, food is where things break down. That's what I love about it, right? No, of course I don't always go out for the cheapest sushi. I mean, sometimes I just want sushi, but sometimes I actually want sushi that doesn't taste like farmed salmon. Maybe you don't eat sushi. That's fine too. Sometimes I just bake the cookies because I think they're better. Whether they are or not, I don't know. So we've been mostly focusing on what we are going to do. We're going to choose the right failure model based upon what we're told the failure modes are. What can we tolerate? And then we're going to design to those. But the user almost never actually gets to choose, unless you are your own user. And this is one of the reasons why people still build distributed systems, because in the end, if you really care, you build it so that it will work for you. Can you think of an industry where having that level of control is important? No? Did anybody who's looking for jobs?
Ads.
Sorry?
Ads.
Ads. Wow. That's right. Ads are mission critical. Must deliver the ads. Okay. That's cool. That's interesting. So I think that I would actually argue that that's an interesting layer of one of the fields, one of the areas I was thinking of. So where else do we actually care? Yeah, airlines are a big one, because if you're tracking aircraft, you might not want to have the database go down for 2 hours. If anybody's looking for jobs in that field, I actually know a company over in Kelowna that's looking for people. So, finance, medicine, hospitals. emergency services, it's almost always either involving money or involving life safety. So the ads is because of the money, right? That's why Amazon cares, honestly. Amazon tries to control these things because they know that downtime actually costs them money. And so they try to minimize the downtime because we want you to be able to shop 24/7. So let's tie this all back. When we looked at Byzantine, we said, what if the nodes lie? We had Byzantine fault tolerance, but there was a very high cost. Who decided we could assume that the nodes don't lie? So that's the interesting thing, is that we think of those as technical arguments, but often the model that we choose to implement is based upon the factors of the product we're building. Or the product that we're building is the one that we think is commercially viable. And so this is the flip side, is that I keep saying, there are people who will pay for these things and they do it, and they definitely do. Government, for example. Now, they have very important things like the Phoenix payroll system. I don't know if anybody saw that, but I think the cost estimate to replace it was $4.5 billion. And I'm like, a payroll system, how hard could it possibly be? Sounds like a big distributed system to me, but I think that this classroom could probably build a pretty good payroll system for a little bit less than $4.5 billion, and probably in less time. When we talked about FLP and CAP, we were talking about constraints on that design space, but those design constraints, the trade-offs there, who's making those decisions? And that's when you start building these, that's a good question for you to ask, because as a technical person, you need to be able to explain to management what the trade-offs are. So the salespeople will come in and they will sell whatever they need to close the deal. And then they'll come back and management will say, well, we just closed this really big deal, and of course we can do all of this stuff, right? And you'll be like going, you want 99.9999% uptime with bounded, guaranteed, strict, linear consistency, and you want to do it on a shoestring. You don't get to do that. That's never a fun conversation. When that happens, my advice is to make sure that you polish your resume and start looking elsewhere. It doesn't usually end well, because management will almost always blame it on engineering. Flexible Paxos. This is a really fun one where you get to choose that quorum size and design. This is kind of an area where most people aren't really even going to understand what the trade-offs are. It's one of the reasons I really think that's a fun thing to understand walking out of here. What do you mean you can choose these different size quorums and come up with different behaviors? I mean, I came up with a quorum. Thank you for the inspiration. I came up with a quorum that allows Mars and Earth to actually keep a Paxos implementation running without dragging Earth down. Pretty cool. And the math is there. It's really easy to see it once you actually model it. There's a whole little PLA plus spec. And as soon as they actually, if anybody wants to see it, I have a paper. I'll put a link or something in Discord. It's a fun paper. It was fun for me, at least. In CRDTs, we're going to talk about what if we design data structures that just simply don't conflict. That's a really cool way of getting out of eventual consistency. It is eventual consistency, but we don't have any conflict resolution. Wow. If we don't have to ever conflict, then things are cool. A couple of years ago, only like four years ago now, I actually saw a presentation of what was called, what were called MRDTs, which were similar to CRDTs, except that it was, they allowed mutations, but the mutations actually had to be commutative. So you could apply them in any order. If you think about like inventory things. Well, we received X of these. And then taking them out of inventory. We sold Y of these, and you can see that those compose perfectly well. And so they were very similar. CRDTs are very commonly used now. This was done by a group at Berkeley 14 years ago, 15 years ago, and basically they've been doing work in that space ever since, because you get graduate students, and graduate students need things to do, so we give them new things in a space that we're still exploring. Anybody going to grad school? Anybody hoping to go to grad school? Anybody naively believing you should go to grad school? What am I supposed to say? And then in lesson 24, next week, we'll talk about self-reporting systems. So, something for you to think about. What did we actually learn here? Failure models are choices. We can build systems based upon those choices. We can make those choices ourselves, but in the real world, they're almost always dictated externally. Eventual consistency shifts costs to the client. Crash fault models assume infrastructure operators are honest and are not going to be trying to cheat. SLAs are business contracts. They don't have anything to do with the kind of safety we've been discussing. Attestation offers some extra level of trust, but we don't trust individual nodes. What we do is we trust the attestation of something. So we have a third party. Testimony versus telemetry is important. So testimony is a claim, telemetry is verifiable computation. Yes, I'm honest. And then he swears that I'm honest. So he's attesting. When I write an expert report for a legal case, I'm very careful, because what I say is, here's the evidence that I reviewed. Here's the evidence I didn't review. If other evidence is brought forward, I may change my opinions, because I'm basing it on what I saw, not basing it upon what the customer paid me. And when I write those reports, I try to make sure that I always can independently verify them as much as possible. I say, I'm saying this, and here's why. I'm saying this, and here's why. So I try to always reconstruct those. And that is essentially an attestation. It says, I looked at these things, this is what they told me, this is how it applies to this particular situation. Impossibility results are really constraints on the design space, and then politics of what restrictions we're allowed to accept is what really defines the contours of that. So somebody, your manager, your CTO, there will be someone who's making that decision. Or maybe you're just going to go out on your own and build these things yourself. All right, there's nothing actually really left to read. There's the unusual self-assessment, the CRDTs, that's pretty much it. And we'll do a short exercise then next week. Next week is kind of a dealer week because, of course, the capstone is due Friday or Saturday. I can't remember which. One is one for class, one for the other class. But the capstone code is due soon, really soon. And then that means I'll get to kick into high gear and get your feedback on that. So next week, like I said, kind of deload week. Don't expect any. It doesn't make any difference with respect to the capstone at this point. So it's more things that are interesting, hopefully. That's it. I'll see you next Tuesday. And next Thursday, I'm not going to have any classes after that. So next Thursday will be the last class. I know technically there's supposed to be classes the following week, but unless somebody wants it. If somebody wants, I can do something. Otherwise, you can just watch the recordings, right? All right.